Okay, welcome to the lecture here. We're picking up on kind of the stoichiometry, molarity, and titrations. So a little bit of stuff from a few different chapters. Again, the notes should be up online if you need them. So obviously in this chapter, as you can see here, we're going to cover all kinds of stuff. So we're going to talk about basic stoichiometry. We're also going to talk about limiting reagents. We then will get into some concentration, molarity, different types of concentration units for solutions. We'll talk about solution stoichiometry and titrations and those type of calculations. All right, so let us get going here. All right, so really stoichiometry is really the place where we sort of use formulas, or not formulas, we use equations and the coefficients from the balanced equations really to do all kinds of problems. But basically, we could figure out from the actual balanced equation, you know, how much products we would make in a perfect sort of situation. If we know how much products that we made, we could also do some back calculations to figure out based on the equation how much starting material or reactants we should have. We could also stay on sort of the reactant side. If we know how much of one reactant we have, we could figure out how much of the other reactant we would need to react with it. And same thing on the product side as well. You know, if we kind of know how much one product we make, if it's multiple products, we could do some stoichiometry basically to calculate how much of the other product that we would get in that particular case. So really, we go from a lot of conversions when we do stoichiometry, but really a lot of it, and there's really kind of four sort of basic steps for a really a basic sort of stoichiometry problem. And really nothing works correct in a stoichiometry problem unless you start with a balanced equation. So you always want to make sure that the equation that you're dealing with is balanced. You then want to take whatever they give you and convert it to moles. So a lot of times you're given things in grams. So then you would want to convert to moles using the molar mass from the periodic table. Once you do that, you really want to do the stoichiometry part, which is the mole to mole relationship. And that does come from the balance equation. So that's why obviously the first step is really important. You got to make sure that it is balanced so that you could do that mole to mole relationship sort of correctly. Once you do that, usually on the back end of the calculation, you usually have to do some type of conversion from moles to some other unit is typically what you have to do. Now, when we talk about sort of stoichiometry and equations, it really is nothing more than sort of conversion factors. And instead of sort of looking up conversion factors in a table or something like that, we really use the balanced equation as our conversion factors. So if we had, say, something like this guy, and we do a 3 there. Now, from this balanced equation, we could really come up with a number of what are referred to as stoichiometrically equivalents or equivalents. And we could say, looking at our coefficients in the balanced equation, we could say for every 3 moles of H2 that we throw in there, we could get out 1 mole of N2. We could also say for every 3 moles of H2 we pop in there, we should get 2 moles of NH3 out. We could also get for every 1 mole of N2, we could get 2 moles of NH3. Now, clearly, as you may know, these are not equal to each other in terms of obviously 1 doesn't equal 2, but they are equal to each other in terms of sort of proportions. And that's really what we're looking at here is sort of the proportion of each of these things that you kind of have to put in there to get out a certain amount of product. It's kind of like when you make cookies, right? You need so much flour, you need so many chocolate chips, butter, and all that kind of stuff. And you need the right amounts of all those things to get like a dozen cookies or whatever it may be. And it's sort of the same idea here when we do stoichiometry here. We need sort of the right ratios of each of these things to basically produce the proper amount of products. And from each of these equalities, we really could write 2 conversion factors. So for example, from the first one, 3 moles of H2 over 1 mole of N2, or we could write the opposite, 1 mole of N2 over 3 moles of H2. For our second guy there, 3 moles of H2 over 2 moles of NH3 are 2 moles of NH3 over 3 moles of H2 and 1 mole of N2 over 2 moles of NH3 are obviously the opposite there, 2 moles of NH3 over 1 mole of N2. So from this one sort of equation here, we basically have 6 different conversion factors that we could use in a problem. And obviously we would not use all of them in a problem. We would want to use the one that would obviously help us get to what we're looking for. And in basic stoichiometry problems, essentially you're given information about one thing in the reaction, but you're actually interested in something else. So you need a way really to go from the thing they're given to the other guy that you're looking for. And again, stoichiometry does that for us. So for example, if I said I started with 4 moles of NH3 and I wanted to know how many moles of H2 I started with, we could do that by starting with our 4 moles of NH3. And then obviously we are interested in NH3 and also H2. So that is our 3-to-2 relationship. So we would want to choose the conversion factor there that's going to allow us to get to what we're looking for. So it's basically a dimensional analysis, opposites. So this guy here would be the proper one to use. That would get us to what we're looking for. So 2 moles of NH3 on the bottom, 3 moles of H2 on top. And we just did stoichiometry there. Congratulations. And that is 4 times 3 is 12. I'm going to try it without the calculator and go with 6 moles of H2 in this particular case. And that's really, all stoichiometry is really just sort of using the equation as a conversion factor to go from one thing in the equation basically to something else. And it really is, in a basic stoichiometry problem, those 4 steps, you always want to make sure the equation is balanced. So if the equation is given to you, you see some coefficients, it's probably balanced, but it's a good idea to check it just in case. If you have an equation, you don't see any coefficients, you definitely should check it and make sure. And then obviously converting grams to moles using the molar mass, very common, and our mole to mole relationship. And then on the back end there, you may have to convert to some other units. Now, sometimes people kind of go backwards. They undo things, and you shouldn't do that either. So if something is already done for you, you should just go on to the next step and not kind of go backwards. Obviously, at this point, if I wanted grams, I would then use the molar mass of H2, right, from the periodic table, and I can convert my moles into grams, and that would be how much technically grams I started with to produce those 4 moles of NH3. Any questions sort of on the basic stoichiometry here? Okay, so why don't you try one here and see what you come up with. Why don't you try this one here? We got methanol, which is this guy, burns according to this equation. How much, we'll go with grams of water is produced here. So how much grams of water? I'll give you some numbers there in case you need. Let's see here. Carbon is 12.01. Hydrogen is 1.008. And oxygen is 16. So give it a go. Follow those steps. Again, balance the equation. Convert to moles. The mole to mole relationship. And moles to some other units. All right, take a couple minutes, give it a go, see what you come up with. I'll try as well. Okay, so let's see how we're doing. So again, we just want to kind of follow these 4 steps here for a basic stoichiometry problem, which this is. So first off, we want to make sure the equation is balanced. So I do see some coefficients, so I'm going to assume that's balanced since there's coefficients everywhere. The second we want to do is take whatever they gave us. So in this particular case, they gave us 209 grams of methanol, which is our CH3OH. And we do want to convert it into moles. So we do need to do that step. So again, that's why we have up here our molar mass from the periodic table. So if we do some adding of all that molar mass there, we got 12.01 plus 4 times 1.008 for our hydrogens and a 16. Looks like we get something like 3204 for our molar mass. So we're going to divide really by that. So that's 32.04 grams per mole of our methanol. And if you want, you could get an answer at this point. You actually don't need to. You could just continue on, but we'll just get an answer here. So I'm going to take it to a few digits here so I don't round too much here. So we'll just go with something like that. 6.5231 moles of our methanol. And that's really sort of the second step here. And the next thing we want to do is find our mole to mole relationship. So basically you want to go to the equation, find the 2 things you're interested in. So one thing is what they gave you, which is obviously our methanol. The other thing is what we're looking for, which is the water in this particular case. And from the equation, we can see that for every 2 moles of methanol, we get 4 moles of water. Again, no real fancy calculation there. It is just simply the balanced coefficients from the equation. That's what we're going to use really for our conversion factor, and that's the big stoichiometry kind of move there. So we'll continue on with our number. And here we do want to get rid of the methanol. So methanol is on top. So to get rid of it, we got to go opposite. We're going to put it on the bottom. So the 2 moles of methanol on the bottom and the 4 moles there of water up on top. Moles are going to cancel each other out. And again, that's the big stoichiometry move. We're going to multiply that by 4 divided by 2. And give us something like, we'll go 13.046 moles of water. So we've now successfully converted into water, but much like usually what will happen is you will always be in moles at this point because you just did the mole to mole relationship. So in this case, we do need to do number 4, which is converting our moles back into grams. Also, we need to remember that we now did the stoichiometry, so we are dealing with water here on the back end. So we need the molar mass of water. So that's your 2 times 1.008 plus your 16. That's 1802 is the molar mass of water. So that would be our last step here. And we're going to multiply here by the 18.02 grams per mole. Moles again going to cancel, and we will end up with, looks like 235 grams of water would be produced in this particular case. This is also what would also sometimes be referred to as the theoretical yield. The theoretical yield is basically the maximum amount of product that you should make in a reaction if everything went perfect. You weren't a klutz and spilled anything or lost anything, no side reactions. That's how much you technically should get out, is 235 grams. Any questions on any of those steps? Again, you do not have to necessarily get an answer after each step. You could have just did it in one big old calculation, which is perfectly fine. If you do individual steps like I did here, kind of like what I also did, is I would not round too much until the end. And in terms of the last answer there, probably our first number there is 3 sig figs. So 3 sig figs on the back end there. But again, there are 4 steps. This is step 1, step 2, step 3, and step 4. And it really is those 4 basic steps when you do a sort of basic stoichiometry problem like this one. Any questions on any of those steps where I got anything?
I had a question.
Yeah.
I just was wondering, 'cause this just seems a lot like study assignment D, but I was wondering what the difference is.
I don't remember what study assignment D was, but was that the moles?
Yeah, yeah. It was like finding molar masses.
Yeah, so it's kind of putting all that together. So it's really putting all those things kind of together. So I think study assignment D was like Avogadro's number, molar masses, moles, and grams, and all that. So it's really putting all those things together, the grams to moles, the balancing equations, and really is sort of putting those things together to do calculations from the equation. So just from the equation itself, or this is called the theoretical yield, is again, if we in theory put in there 209 grams of this methanol, everything went perfect, nothing bad happened, no side reactions, 100% of the reactions was sort of completed, we should in theory get 235 grams. And that's sort of what all this is putting all those sort of concepts together to allow you to figure out things like that, like how much product you should produce. You could also kind of go backwards, like we talked about. You know, if you know how much product you produce, you could predict pretty much how much reactants you had to do. So it is similar. You have to do a lot of those things, like converting to moles is very common in these type of problems. Converting from moles back to grams on the back end of the calculation is also very common. So it's sort of like a continuation, putting all those sort of concepts together, the last few that we've been talking about.
Got it. Thank you.
Yep. Other questions? Okay. Let me try one more sort of basic stoichiometry problem here. There's that. There it is, and all in one step in case you want to see it in slow motion. You can watch it later when you watch these recordings to go to sleep, I suppose. But let's go back here and try a different one here. Let's get that. So let's try another one just to make sure before we go on to a little bit more complicated ones. So let's just steal that reaction that we used earlier. We'll do this one. So let's go with how many grams of H2 would we produce? I'm sorry, would we start with? Would we start with? If we produced, let's go with 125 grams of NH3. All right, with my bad scribbling here, obviously end of the week, can't write anymore. All right, so we want to know how many grams of H2 we would start with if we produce 125 grams of NH3. And again, some numbers that would probably be helpful, 1.008 and nitrogen 1401. So take a couple of minutes here and see what you come up with.
Hey, Professor Efron.
Yeah.
I had one more question about that last problem.
Yeah.
Um, so I did it in one long chain, like you said was okay.
Yeah.
So what I had done is, you start out with the 209 methanol, and then I divided by double the grams so that I had 64.08 over 2 moles of methanol.
Yeah.
So that way the mole ratio is okay. So do we have to like worry about that mole ratio?
I would recommend breaking that apart and doing it separate. So technically speaking, math wise, you're going to end up with probably the same if you kind of do it right, if you do it that way, kind of correctly. But technically speaking, when you go for something like the molar mass here, the molar mass is always per 1 mole. So you should always do it just based on the formula. So even though there's like a 2 here or something like that, you really shouldn't kind of include that in the molar mass part of the calculation. You should kind of do it in a separate part, which is the stoichiometry part down here. And again, sometimes, if you don't do it maybe correctly, sometimes I've seen people kind of do it twice, or not do it once and kind of do the calculation twice. So you take into account that too. So sometimes people do what you just said you did, and then also then do the 2 here, and then sometimes it kind of messes up the calculation. So it's really good practice whenever just molar masses for something, for example, even the like 2 of the CO2s, it's always based just on the formula, because it's always based on 1 mole of these guys. So you should always, when you're doing kind of the molar mass part, just do it based off the formula. And then if you're doing something like what we're doing here, then take the stoichiometry into account in sort of that separate sort of step. Because otherwise, I won't say it's 100% wrong, but it's really not the right way to do it, because a lot of times people will kind of screw that part up. They'll do it twice or something like that. So they'll do
Yeah, I did it twice and it worked out. So
Yeah.
I didn't know. That's weird. So it shouldn't have worked out?
It really shouldn't. If you then did this part of it, it shouldn't have worked out really. I don't think. Yeah. So if you also have this step in there, you're kind of doing that part twice, because that's really what this part is for. This part is to take into account kind of how many you have in the equation, the stoichiometry part. So if you doubled this and also doubled this, it probably shouldn't come out correct, in that sense. The reason it did come out correct is
It's because I doubled the bottom.
because you doubled the bottom and then you also doubled the top. So
Yeah, okay. That makes
sense. Cancel. But sometimes very common people don't double the top like you did.
I see what you're saying.
And they go like, hey, there's 64 grams per mole type of thing.
Right. Which is
and they don't kind of double the top. So in your case, it worked out because you actually did the top. So that's why I would recommend not kind of trying to combo those 2 steps together, kind of keep them separate. So just in case, you don't mess up like that. So that's a common thing people will sometimes mess up
on. All right.
Yeah.
Thank you.
For the H2, the mass would be 2 times like 1.008, correct?
Yeah. So let's talk about this. So when we're doing something like molar mass and you want to go to the periodic table, it is always based on just the formula part. So in that case, that's why we would take the 2, and it would be 2 times the 1.008 there in that case. Yeah.
Would that be hydrogen gas then, H2?
It would be technically the
Okay.
gases. Yeah. That's
Okay.
H2 and that's N2, and that's ammonia gas actually on that side as well.
Okay. Thank you.
You're welcome. Okay, so why don't we take a look at this one here and see how we're doing. So again, we're looking for how many grams of H2. So we're actually coming here at the end. We're starting with the NH3, which is over there on the right-hand side. And again, here we just want to follow those 4 steps for these type of problems. So we do have a balance, so that's good. Number 2 would be take whatever they gave us really and convert it to moles. So in this case, we are given 125 grams of NH3. And again, here, when we go to do molar mass, really important, because I've seen people really kind of mess up on that part. Again, it is just the formula here. So even though there's a 2 here, we're going to take that into account with the stoichiometry part. So the proper molar mass for NH3 in this case would be our 1 nitrogen at 1401 plus our 3 hydrogens at 1.008. And that gets us something like 1703, I believe. That'll be 1703 grams per mole. And again, that's the key part of molar mass. It is per mole, and that's why you should always just do it based off of the formula and just the formula of it, regardless of how many numbers you have in front in a balanced equation. Because again, you're going to take care of that part later on in the calculation. And as we were talking about there earlier, very often people don't do that part right, and they end up getting sort of the wrong answer. So here we're going to convert our grams into moles using that 1703 grams on the bottom, a mole up on top. The grams will cancel. And again, like I said before, you don't necessarily have to get a number, but I'll just do it kind of step by step so you can kind of see the different steps here. And again, I'm just going to take the number to a few digits down the road. And that gives us moles of NH3. Once we have that, we then want to go to the equation and find the two things we're interested in. So I put some boxes on it there. So from the equation itself, we could see that for every 3 moles of H2, we get out 2 moles of NH3. And again, we're going to use that relationship as our conversion factor. So we'll go with 7.33999 moles of NH3. Again, opposites cancel, so we want to get rid of the NH3. So up on the bottom there, we'll go 2 moles of NH3. On top, we'll go 3 moles of H2. And that's the stoichiometry part. That's the part's going to cancel out our moles of NH3. And that will get us, and again, here, if we did get an answer, something like 11.01. And now we have converted to moles of H2 in this case. So it's 2 moles of NH3 because that's from the balanced equation. So that's the mole to mole relationship. So it's 3 moles of H2 and it produces 2 moles of NH2. So when we do that kind of mole to mole relationship, it is just the coefficients from the balanced equation. So that's why it's really important to start with the balanced equation so you have the right coefficients and the right relationships. At this point, we do want to get to grams, so we do need now the molar mass. And as was asked earlier, again, here we would just do the molar mass for H2 based off of the formula. So that would be 2 times 1.008 grams per mole. And that gets me something like 2.016 grams per mole. Again, here we don't want to do the 3 with our molar mass because we already did the 3 over here. And it's very common people will not kind of do that part correctly. So you don't want to kind of combo those steps. So 2.01 on top grams of H2 on a mole of H2 there on the bottom. And if we do all that good stuff here on my made up one, it looks like got something like 22.2 grams of H2. Now, this would not be a yield, a theoretical yield, because it's a starting amount. But this basically tells us that if we did this reaction and we produced about 125 grams of NH3, we should have put in there about 22.2 grams of H2 to basically yield that. Any question on any of those steps? And again, you could kind of see here, same basic 4 steps. Step 1, step 2, convert to grams to moles. Step 3, mole to mole relationship from the balanced equation. And step 4, convert our moles into some other unit. Any questions on any of those steps there? So remember, in stoichiometry, as we did in the first one, we could go from reactants to products. As we did in this one, again, we could go from products back to reactants. And we could also, again, just stay on the same side of the arrow. You don't necessarily have to cross over. And you could do a multiple relationship in stoichiometry. Same thing on the product side. If we had 2 or more products, we could also do some stoichiometry between those guys as well. Any questions on sort of basic stoichiometry type problems here? Okay, so when you have this basic stoichiometry problem, the way you know it really is sort of a basic stoichiometry problem is basically you're given only one piece of information. So you're given, the starting amounts, or you're given the amount of product, but really only one information that it will allow you to get the moles. So if you're just given enough information to only get the moles of one substance in a reaction, that is really a basic stoichiometry problem, and you should follow these 4 steps. Now, there are more sort of complicated stoichiometry problems, and these involve what are sometimes referred to as limiting reagents. So let's talk a little bit about those. Here. So in normal reactions, there is usually some type of reactant that pretty much gets used up first. And when that reactant gets used up, you pretty much cannot make any more products. And that reactant that gets used up first is what is known as the limiting reagent. So the limiting reagent is the reactant that gets used up first. While there's usually another reactant that you have plenty of, and that is what is known as the excess reagent. So the excess reagent is the one you got plenty of. It's in excess. It will actually still be there technically when the reaction is over. So the limiting reagent is the one that gets used up first in a reaction. The excess reagent is the one that you have plenty of. You have some left over when it's all said and done. So if we look at sort of these pictures here, the blue and red is the NO, which is a reactant. The O2 is the 2 red circles. And we can see that when the reaction is over, we have no more red and blue circles together. So the NO is our limiting reagent. The excess reagent is our O2, as we have a number of O2 molecules basically left over when the reaction is done. We could even, if we wanted to, count how many of these limiting excess reagents we have left over when it's all said and done. So why is limiting reagents important? Well, limiting reagents are important because once you are done with it, you cannot produce any more products. So a very simple example is if you take A plus B to make AB, as soon as you run out of A, you can't make any more product because you're missing a crucial part of it, right? So when we're trying to determine basically how much product we're going to produce, it is always the limiting reagent that's the most important. It is the limiting reagent that determines how much product you can make, because it pretty much as soon as that is done, you're not going to be able to make any more product. So when we do limiting reagent problems, and to be honest with you, there's multiple ways you could do limiting reagent problems. I'm going to show you a way that might be new to you, that might be good as well. But there are other ways that you could do these type of problems. But in the basic sense, it's a lot of the same steps that we were just talking about. The only additional thing is somewhere along the way, you need to determine which one is the limiting reagent. So somewhere along the way, you kind of have to determine kind of which one is our limiting reagent. So when we do these problems, how you know it's not a basic stoichiometry problem, but it's more a limiting reagent problem, and somewhere along the way you need to determine that limiting reagent, is based on what's given to you. So in limiting reagent problems, you're usually given enough information to calculate the moles of both reactants. So that is a big hint that this is some type of limiting reagent problem, because you pretty much were given enough information to actually calculate the moles of each of the starting material. And that's again how you could distinguish this type of problem from just a basic stoichiometry problem. Any questions on that? It's kind of like you buy hot dogs and you buy hot dog buns. They give you like 8 buns, right? But the hot dog package got 10 hot dogs or something like that, right? So your buns are your limiting reagent. Hey, it's dinner time. We're going to try that for our example here. But yeah, so you're going to run out of buns, right? And that would be your limiting reagent. You would have 2 hot dogs left over, which would be, hey, how much excess reagent you have when it's all said and done. All right, class field trip. Let's go get hot dogs now. All right, so let's talk about how to do these problems here. And I'm going to show you a way to do these problems, which, well, I think is a good way because oftentimes will allow you to very quickly calculate a lot of things that are asked in these type of problems. Now, you don't have to do it this way. If you don't like this way, it's you won't hurt my feelings. You could do it some other way if you remember how to do it or you learned a different way. They all really should get you in sort of the same answer when it's all said and done. The nice thing about this, like I said, is very quickly you can really calculate a lot of things that you're very commonly asked about in these type of problems with a lot of not so much extra calculations involved. Now, also a benefit to the way I'm going to show you is it's pretty much if you plan on taking 200B, it's kind of the calculation you're going to do all day, every day there in 200B. So it's very similar to those type of calculations. So it might help you out if you're going on to 200B. So again, if you learned about limiting reagents previously, which you might have if you took the previous class, and you remember how to do it that way, you can do it that way. I'm going to show you a different way, and we'll look at an alternative way of doing it as well, which I think I have. So we'll kind of look at both ways. And again, you could choose whichever way you want to do it. Like I said, there's probably like 3 or 4 different ways you could kind of do these type of problems. All right, so the approach we're going to take when we do these sort of limiting reagent problems is what is sometimes referred to as an ice table approach. And when we use ice tables, ice stands for I is initial, C is change, and E for us will be end. If you take 200B, it'll be equilibrium, but kind of the same idea here. So the first couple of steps in this sort of type of problem is really the same approach as before. You still want to make sure that the equation is balanced. You also want to make sure you convert whatever they give you into moles. So first off, the reason we do know, by the way, that this is a limiting reagent problem is here we are taking 124 grams of aluminum and we're reacting it with 601 grams of iron 3 oxide. So I have grams of aluminum and grams of iron 3 oxide, and those are both of my reactants. And they gave me the grams of each of those, which means I definitely could get to the moles of each of those things. And that's the key, that this is a limiting reagent problem. You're given the starting amounts of both reactants and enough information basically to get to moles of both reactants. So first step is still kind of the same. We want to make sure it's balanced, which it is. Next step is we want to convert each of these things into moles. So we're going to take our 125 grams of aluminum. We're going to convert that into moles from the periodic table. We got there 26 something, 2698. And that gives us 124 divided by 2698. And again, we're going to go 4.596 moles of aluminum. We're also going to convert our grams of iron 3 oxide into moles. So same idea here, regardless of what we see in the equation, we're going to do the molar mass based off of the formula. So that is 2 times iron's molar mass, which is 5585 looks like. And 3 times 16, which is the molar mass from oxygen. And that gets you a lot there, I'm imagining. We've got about 159.7 grams per mole. All right, so we're going to use that again really as our conversion factor here. So the grams are going to go on the bottom, 159.7 over moles. And that gives us a opening moles there of, not that, try that. There you go. About 3.763 moles of our iron 3 oxide. So again, kind of the second step is still really the same here. Now the third step here, we're going to kind of do different because it is a limiting reagent. Here's where we're going to do our ice table. So to do the ice table, you're basically going to start with the balanced equation. So we're going to rewrite our equation here. And we're going to start with initials. So initial is basically the starting moles that we got going on. So initially we calculated that we have 4.596 moles. And for our iron there, we had 3.763 moles. And initially you could assume that you have 0 of your products. Now, we could also assume, as we see here with the arrow, that the reaction is heading from reactants to products, which means as this reaction goes on, the amount of reactants should decrease, the amount of products should increase. So the change part is usually represented by X. You can really use any letter you want, but why not use X? So we're going to use X to represent the change that's occurring here. Now, very important here is we need to also take into account our coefficients when we do this. And when we take into account our coefficients, that does all that wonderful mole to mole relationship, that stoichiometry part for us. So on our reactant side, this is going to be minus 2x, the 2 for the coefficient in front of the aluminum. That takes care of the mole to mole relationship. Next is going to be minus x. Again, the coefficient in front of iron 3 oxide is 1. On our product side, that's going to be plus x. Again, coefficient here is 1. And we're going to have plus 2x for our iron on the product side. Again, the coefficient there is 2. So the importance, again, of that is to make sure you include those coefficients. Really what that does is that mole to mole calculation that we do in a traditional stoichiometry problem. Any questions on that so far?
Do we not care about phases?
For what we're doing here, not particularly. You could put them in. It really has no bearing on sort of the calculation or anything like that. So that's why they're probably left off here. But you could put them in if you want. It won't make that big of a difference. Pretty much, first guy, the aluminum by itself would be solid. Iron on the back end would be solid. The other two probably be something like aqueous and stuff like that. All right, so what we're going to do at the end part here is basically carry down everything. So on the bottom here, we're going to have 4.596 minus 2x. I'm just going to take the moles out for now so I don't have that moles kind of in the middle. 3.763 minus x, x, and 2x. So again, here we're just going to carry down everything. And if you want, you can leave the moles in there, or just remember that we're dealing with moles here if you want. All right, so now we're going to come to the part where we're going to figure out which one is the limiting reagent. So to figure out which one is the limiting reagent, we're pretty much going to take our two reactants and we're going to set each of them equal to 0 and solve for x. So if I do that, 4.596 minus 2x equals 0. And if I solve for x in this case, we're basically just going to divide by 2. So 4.596 divided by 2 gives me 2.298. And these are moles, by the way, when you solve for x. If I set this guy equal to 0, x is going to equal 3.763 moles. Any questions on that? So again, just bring the 2x to the other side, divide by 2, gets you both of those. So this little calculation that we're doing right here is going to allow us to determine which one is the limiting reagent. The limiting reagent is the one with the smaller number. So the smaller number, which means this is our limiting reagent. So we could kind of cross this guy out. We don't really need him. So what that means is in this particular reaction, the aluminum is our limiting reagent. And by default, that would mean that our iron 3 oxide would be our excess reagent. So once you're able to determine which one's the limiting reagent, the other guy would be your excess reagent. Any questions on that right there? Okay. So the nice thing is, and why sometimes this approach is kind of good in a lot of questions, is we have now just determined what X is. So this X is every single X here in this table. What that means is relatively quickly, you could pretty much answer any question that you're asked. You could figure out how much of each product you made. You could figure out how much of the excess reagent is left over pretty quickly in some calculations. So to show you how to do that, I'm just going to flip the page because I'm on the bottom of my page here. I'm going to rewrite that real quick here. So I'm just going to kind of rewrite the equation and what we got going. So we got this ice table here. And I'm just going to just focus on the equilibrium part. So at the equilibrium here, we had 4.596 minus 2x. We had 3763 minus x, and x and 2x. Okay. And we just determined that x is equal to 2298. All right. Okay. So we'll start with the actual question that it asked in this one was, how much of our aluminum oxide did we produce? So we see that at the end of this reaction, our aluminum oxide equals X. So that means that the moles of aluminum oxide equals X, which means that we had produced 2.298 moles of aluminum oxide, which we can then convert into grams by using the molar mass of aluminum oxide. So we would go to the periodic table, and that is 2 times 2698 for the aluminum, plus 3 times oxygen, 16, gives us 101.96 grams per mole, again, from the periodic table of aluminum oxide. And we times that by our 2.298, tells us that we have produced here 234 grams of aluminum oxide. That would also be known as the theoretical yield of aluminum oxide in this reaction. Now, that was what we were actually looking to solve for here in this particular reaction. But the nice thing about this table approach is it wasn't asked, but we could then very quickly figure out how many grams of iron we actually made, because we know that the moles of iron from our table is equal to 2 times X. So it's equal to 2X at the end, which means that we would take 2 times our X value, 2.298 moles of our, what we got there, iron. And that would tell us that we would have produced 2 times 2.298. That would give us 4.596 moles of iron. And then we could go to the periodic table and look up iron's molar mass, which is 5585. And it would tell us that for iron, if we were also curious about that guy, we produced about 257 grams of it, which would be the theoretical yield of iron in this particular one. So very quickly, as you can kind of see, we can, without sort of rebooting from the very beginning, figure out how much of the other product that we produced. Any question on those two calculations so far? Okay. Now, an added benefit of doing this approach is it is very commonly asked how much of your excess reagent is there. So how much of your excess reagent is left over? And normally, depending on how you do these type of calculations, if you kind of don't do this approach, you got to kind of go back to the beginning and do a few more calculations. But for us, we know that our excess reagent is our iron 3 oxide, which we could see from our table that our iron 3 oxide, when it's all said and done, is equal to 3.763 minus X, which means we have 3.763 minus our 2.298 moles. And that tells us when this reaction is over, we have 1.465 moles of our iron 3 left over, which we also could use the molar mass that we calculated earlier. So I'm just going to steal that real quick. What was that earlier? That was 159.7. And we calculated that earlier. And that tells us that we have 159.7, about 234 grams of our iron 3 oxide left over. So if you remember, we started with what, 600 grams of it or something, 601 grams of the iron 3 oxide. We used about 300 and some odd grams of it in this reaction. So we have 234 of it left over. How much of our aluminum should we have left over? I won't put it in there, but it is the limiting reagent, which means we should have 0 of that left over, right? So if you put that number back in, it should end up at 0. So this approach here is one way that you could kind of do limiting reagent problems. Again, really the benefit of it, other than the fact that you'll do this calculation nonstop in 200B, but the benefit of this is really you could really kind of quickly solve for anything that's typically asked of you in these type of problems. So typically asked is how much of each product you produce. Also very typically asked is how much of your excess reagent is left over. Any questions on kind of where any numbers came from, why I did any of those things? Is my internet going to die so this lecture will be over? Any of those questions? Oh, yeah. All right. I see smiles, so that's good. At least you can still hear me. I suppose I'm not muted. All right. So again, this is one approach. And again, if you sort of learned a different approach, you could still do that. If you like it better, it should come out the same. Common ways that you kind of can figure out limiting reagent problems is to do 2 separate stoichiometry problems, starting with each reactant separately and figure out how much product each reactant produces. And the one that produces the smallest amount of product is your limiting reagent and also your theoretical yield. You could also do some other type of calculation where you do a calculation to figure out how much of one reactant you need to use up the other reactant. So those are other common ways. So I think I have this problem worked out a different way, and I'll just kind of scroll through it so you can kind of see it. And again, if you want to kind of review it, you can look at the video, but I'll just kind of walk you through it. So this is another sort of approach here. And the approach that they did here was they took one of the reactants and they basically figured out how much of the other reactant they would need to put in there to use it completely up. So what they chose is they wanted to use up all 124 grams of the aluminum, and they did just a stoichiometry calculation between these two, which is a very common approach as well. And they figured out that they would need to throw in there 367 grams of the iron 3 oxide to do that. And they know that they do have enough because they're starting with 601 grams. So what that would tell them from this calculation is the exact same thing that we figured out, that this is our excess reagent and this would be our limiting reagent, because we did have enough to put in there. We needed 300 some odd grams. We have 600 to start with. So that would determine which one's the limiting reagent. And basically what they would do at that point is start a new stoichiometry calculation with our limiting reagent going to our product. And that's what we'll see here. So they start with our limiting reagent, doing our limiting reagent to our product and figuring out how much product we would have made. And you can see here, you get the exact same answer that we got, 234 grams of aluminum oxide. So this is, again, another very common way where you take both reactants and you do a little calculation to figure out how much of the other reactant you need to completely use up the first guy, and see if you have enough. And if you do have enough, like it was here, that would be your excess reagent. If you don't have enough, that would be your limiting reagent. And you can then use your limiting reagent to figure out how much product you make. Again, the third most common way is like I mentioned before, basically just do two old straight stoichiometry calculations, one like this, and then one with the iron 3 oxide to the aluminum, and figure out which one produced the smallest amount, and that would be your limiting reagent. So there is 3 different ways you could do this problem. Again, you could choose whichever way that you want to kind of do it. The sort of non-benefit of doing it this way is, as you can see, if you want to figure out all the other things that we talked about, you then sort of had to go back and then do the one for the iron to figure out. You then have to kind of go back and figure out how much of the iron 3 oxide you used up to figure out how much of the excess is left over. So there's a lot more kind of back calculations you have to do if you kind of do them separately. So again, the ice table sometimes will kind of put it all together for you in a very quick way. Any questions on that? Okay, so let's talk about yields. So there are really 3 types of yields. There's the theoretical yield, there's the actual yield, and then there's the percent yield. So the theoretical yield, as we've talked about, is really the amount of product that you should make based on the equation, the stoichiometry, and how much you're starting with. So in our calculations there, the 234 grams of the aluminum oxide was our theoretical yield. How much product that you make is your theoretical yield. That is your maximum yield. That is like what we were talking about earlier. Everything went 100% perfect. You weren't a klutz. You didn't spill it on the floor. You know, you didn't lose something along the way. Everything went perfect. That is, in theory, how much you should get out. But life happens and actual yields happen. And actual yields is actually, much like it sounds, what you actually got when you physically did the experiment. So in most cases, most reactions don't really work perfectly all the time. Maybe just think logically about things. If you're doing a reaction, you're scooping out things, right? You maybe don't get everything out of the beaker. Maybe some stuff stays on the spatula or something like that. You know, there's a lot of places in reactions where you could kind of lose things along the way. So the actual yield is actually how much product you produce when you did the reaction. In sort of textbook problems and things like that, that is usually given to you. So that's usually given to you somewhere in the problem. And usually you have to figure out the theoretical yield. So figuring out the theoretical yield may just be a regular stoichiometry problem. It may be a limiting reagent problem, but somewhere you need to figure out usually the theoretical yield. And then you get everybody's favorite, which is the percent yield. And that is the actual yield divided by the theoretical yield times 100%. And that is basically how good you did in that reaction. So when we talk about percent yield, we actually want a high number. So near 100, high 90s is usually pretty good. We don't really want a low number. So you got like a 2% yield. You didn't do so well there probably in that reaction. So if you got kind of a high percent yield, you did pretty good in that particular reaction. So can you get above 100% yield? And the answer is yes, but that's probably not a good thing either. That usually means you kind of screwed up somewhere. So you usually shouldn't get over 100% yield, but it can happen. A very common way that happens is sometimes when people do reactions, a lot of times they filter out, say, a solid or something like that. And when they're filtering it, they put it on some, say, filter paper. Filter paper is still wet. The product's still wet, and they weigh it again. And you get all that extra water weight that's really not there. And that sometimes will cause a kind of high percent yield that occurs. So usually you shouldn't get over 100%. Usually that's not a great thing. That usually means something didn't go so right. But you do want to get, you know, near 100%. Like I said, high 90s is usually pretty good. But a low percent yield is not so great. Any questions on that there? All right, so why don't you, you know, give this one a go, see what you come up with. So we want to calculate the theoretical yield of Ti and also the percent yield if we yielded 5.42 times 10 to the 6 grams. So take a few minutes here, see what you come up with. So 2 answers there. What is your theoretical yield and what is your percent yield? And it looks like they were nice enough to give us some molar masses, I think. Yeah. I'll give you a TI, which I think is 4788.
So this is an example of a limiting reagent.
Yeah, so you got to determine if it is a limiting reagent a problem or not. So if you look at it, I'll give you the hint here. They do give us grams of TiCl4 and they do give us grams of magnesium. So technically we do have enough information to get the moles of each. So it definitely is a limiting reagent problem in this case. Yeah.
Once we have the limiting reagent, how how are we supposed to find the theoretical yield of titanium?
So if you do the ice table, you want to do the ice table and then solve for whatever it is in the ice table at the end. So you'd always want to do kind of a stoichiometry problem from the limiting reagent to whichever one you're trying to solve for, which is sort of what, if you're not doing sort of the ice table approach. Okay, so let's see how you're doing here. So as we talked about at the beginning here, we do know it is a limiting reagent problem because, again, we're given enough information about both reactants here to basically get to moles. And that's sort of the key to figure out that it is a limiting reagent problem. So we do need to figure that out at some point, and you could do it, again, whichever approach you're comfortable doing it with. First couple of steps, still the same. We want to make sure it's balanced, which I believe it is. We then want to take what they gave us and basically convert them into moles. So they gave us that we are 2.46 times 10 to the 7 grams of TiCl4. They were nice enough to give us the molar mass. Again, if they didn't give us the molar mass, we would get that from the periodic table. And that's basically 189.7 grams per mole here. And that gave us something like 1.3 times 10 to the 5 moles of our TiCl4. We would also want to convert our grams of magnesium into moles. So using that number here, also you want to make sure that you are using your exponent button, right, when you punch these guys in. Also, they gave us the molar mass from the periodic table, which is 2431, it looks like. And that looks like it gets us something like 4.65 times 10 to the 5th moles of magnesium. So again, really, no matter what approach you take, kind of the first two steps are pretty much the same. You got to convert to moles, got to make sure you got a balanced equation. Any questions up to that point there? So again, I'm going to show you it through the ice table approach just to show to you again. So what I'm going to do is basically start with my ice table. So we'll start with our excuse me, equation here. So we got TiCl4 plus our couple of magnesiums going to give us our Ti plus our couple of magnesium chlorides. So here we're going to again start with our initial moles. So we calculated that we had 1.3 times 10 to the 5 moles. For magnesium, we had 4.65 times 10 to the 5 moles. So remember not to use such big numbers next time. And on our product side, we'll just assume 0 there on our product side. Again, you could pretty much safely assume that it is going to head to our product side. So here's our change part. And remember, we're going to represent that with X's. So our reactants should be decreasing. So that's minuses, and products should be increasing. That's pluses. And also important, we want to take into account our coefficients in this step, because really that does the stoichiometry part. So if you don't do that part of it, you're not doing the mole-to-mole relationship and you will get the wrong answer. So this is going to be minus X because coefficient is 1. This is going to be minus 2x. Again, the coefficient here is 2. On our product side, this will be plus x and plus x. And that means when we get to the end here, we're just going to carry those numbers down. Again, I'm going to get rid of the mole part so I don't have so many words in between my numbers here. So this is going to be 1.3 times 10 to the 5 minus x. This would be 4.65 times 10 to the 5th minus 2x. Carrying this down, this would be x. And this should be 2x, as I missed the coefficient there on the back end. So that should be actually 2x there at the end. Any questions on the ICE table? See? And again, importance, although we're not going for magnesium chloride here, if I left that 2 off, I would end up with the wrong answer because, again, I would not have the correct mole-to-mole relationship. So once we got sort of our ICE table here, we want to, again, set our 2 reactants equal to 0 and basically solve for x. So 1.3 times 10 to the 5th minus x equals 0. That means x equals 1.3 times 10 to the 5th moles. And again, when you solve for x, it is moles. This is 4.65 times 10 to the 5th minus 2x equals 0. We're basically going to add the 2x to the other side and then divide by 2. So that's going to give you 4.65 to the 5th divided by 2. Gets us something like x is equal to 2.33 times 10 to the 5th moles. So what we're looking for here when we solve for x is it is the smallest number is our limiting reagent. So this is our smallest number. And that means that this is our limiting reagent. So we don't really need this number at this point. Again, that means in this case, our limiting reagent is our TiCl4. Our excess reagent is our magnesium in this particular case. Any questions on up to there? Now, in this particular problem, we weren't necessarily asked for everything, but a reminder that the x value we just got is every single x in this table at the end. So in this particular case, we are interested in Ti. So if we go to the table, we see that Ti at the end is equal to x. So for our moles of Ti, that would equal x, which means we have made 1.3 times 10 to the 5th moles of Ti. We can convert those into grams by using the molar mass from the periodic table. And that was 47, I said, right? 47.88. And that will give us, for our Ti, 6.22 times 10 to the 6 grams of Ti. This technically would be our theoretical yield here. Any questions on that particular one there? Again, we weren't asked, but we can, as we talked about last time, very quickly, if we needed to, figure out how much magnesium chloride we would have by just taking 2 times the x value. We could also, for our excess reagent, stick the x back into here and figure out how many moles of our excess reagent would be left over as well. So again, the benefit of this sort of approach is you could kind of answer those questions really quickly. But we'll stick to what it's actually asking here, and we want our percent yield. So our percent yield is our actual yield divided by our theoretical times 100%. So we just got our theoretical yield. And as I mentioned before, usually given to you in the problem is our actual yield, which it was here. So basically, we're just going to divide those two numbers. So that's 5.42. So 5.42 times 10 to the 6 divided by our theoretical 6.22 times 10 to the 6 times 100%. And that gets us something like
I got 87.3.
Sounds good. I'm putting extra negatives in my numbers and having that dramatic pause, but I agree with you. 87 point, what did you get there? 14, 13, something like that, depending on your rounding. And that would be our percent yield in this case. Not too bad, 87%. It's decent. Probably in terms of numbers and sig figs, probably 87.1, as we started with pretty much everything with 3